We are in fact going to at least get started today. I doubt very much we'll get 5.3 finished, but at least I'll get enough done for you to do some of the homework questions. We are going to spend the beginning of today finding antiderivatives, which should have been the last thing you did in Calc 1. That's typically the last thing you do in Calc 1. And once we've done enough practice on that, I'm then going to show you a guy called the Fundamental Theorem of Calculus, Part 2. Sounds like a movie. That actually will allow us to find the area under a curve. And it'll be amazing how simple it is to find the exact area under a curve. And that's going to be the important thing. And then we're going to do a couple of little side things because they're in the homework and they are part of it. We're going to look at the Fundamental Theorem of Calculus Part 1, which, to be honest, is not very useful. But it's there, so we'll show you. And then we're going to do a thing called area functions, which are okay. So let's start by looking at antiderivatives. Now, if I gave you a function f of x, and I told you it was, what, 4x cubed, and I said to you, what is its derivative? Well, you use what's called the power rule, right? You multiply by the power, and you reduce the power by 1. And when you go in that direction, we call that process differentiation. So you all should be quite familiar with derivatives, right? Remember the power rule, multiply by the power and reduce the power by 1. That's essentially what I did here. Now, suppose I gave you 12x squared, right? I gave you this, and I said, look, the answer is 12x squared. What function would you need to start with so that its derivative was 12x squared? And when you go in this direction, we call that finding the antiderivative. Right? It's the opposite of differentiation, right? Antiderivative. Okay. So we're going to get some practice at finding antiderivatives. And I'm going to introduce you to some notation. Our original function is still going to be called f of x, and this particular one is going to be 4x squared. And we are going to find its antiderivative, and the typical notation for antiderivatives is to use the capital of that. So the antiderivative of f of x is called capital F of x. Now, don't think differentiation. Try and think the opposite of differentiation, right? What function would I need so its derivative was 4x cubed? Anybody want to have a shot at it? For instance, what would the power of x have to be?
X cubed.
Now, when you've got x cubed, which is correct, what do you do with that new power, the 3? Do we make it 3 times and turn it to 12, or do we make it 4 divided by 3 and call it 4/3? Because there's really only 2 ways to tackle it, right? What do we do with this new power 3?
We divide the 4 by 3.
Now, if this is correct, and it is, shouldn't the derivative of that be 4x squared? Great. Let's check it out. If you multiply this by 3, you get 4, and reduce it by 1, you get x squared. It works. We also add a little guy called plus c. It's called the arbitrary constant. And the reason that you need that plus c is, couldn't 4/3 x cubed plus 7 and 4/3 x cubed plus 70, won't both of them give you this as a derivative? So any number at all, any arbitrary constant, could also work. So the antiderivative isn't a specific one function, 4/3 x cubed. It's a whole family of them. 4/3 x cubed plus some unknown number called c. Try another one. I'm going to put the f of x here. and its antiderivative here. Okay, how about 5x to the 4? What would the antiderivative of 5x to the 4 get me?
X
Yeah,
to the
let's take
fifth.
it in stages. And add 1 to the power, yep, and divide by the new power. So in general, if you want to find the antiderivative of any multiple of a power of x, right, a 5x cubed, 4x squared, right, there is a rule, it's actually called the power rule. So it's got the same name that the power rule in differentiation has, but it's usually a different rule. You add 1 to the power, and then you divide by the new power. So if you wanted to do 5x to the 4, you add 1 to the power and then divide by new power. Let's pick some random guys. 10x cubed, antiderivative. Add 1 to the power and divide by that new power. If you need to, sometimes you do. Oh, and don't forget your pluses. How about this fella? 7x cubed plus 2x squared plus 4x plus 3. So basically a polynomial. Now, if you want to find the antiderivative of a polynomial, just find the antiderivatives of each piece. That's all you need to do. Now, I've deliberately chosen some really ugly answers. 7x cubed. If you add 1 to the power, you get 4. And if you divide by the new power, you get 7/4. Next door. 2x squared. Add 1 to the power, x cubed. Divide by the new power. Next one. 4x. Add 1 to the power, you get 4x squared. Divide by that new power, you end up with 2. Now, a new guy in time. What is the antiderivative of a number like 3?
3x.
In fact, won't 7 get you an antiderivative of 7x and 20 get you an antiderivative of 20x? So a number on its own, basically, its antiderivative, you just add an x to it. Do you feel comfortable now that if I gave you any polynomial, right, anything that looked like this, you feel comfortable enough now that you'd be able to do its antiderivative? Have we got the cobwebs out your head? You're up to speed on that. Okay. So let's make life a little bit more difficult. Let's try and find the antiderivative of that guy. Now, if you want to find its antiderivative, it's a good idea, if it's possible, and it is in this case, that you rewrite it as a power of x, even if that power is negative. Are you comfortable that 10 over x to the 4 is the same thing as 10x to the negative 4? You probably did that in Math 94, at least if you did Math 94 here. Now, the reason why you want to write it like this is, do you see this power rule? Add 1 to the power and divide by the new power. It even works when the powers are negative numbers, right? So it doesn't just work for x cubed, it works for x to the negative 4 as well. So its antiderivative, capital F of x, is going to be add 1 to its power. Trick question coming up. So be careful with your answer. What do you get if you add 1 to negative 4?
-3.
Correct. Do you know one of the most common mistakes that people make? -5. 4 becomes 5, right? But isn't it -4 add 1, right? You're adding 1 Temperature's increasing a little bit. Now that means you are now going to divide by the new power, which is -3. So do you see how ugly that answer is? But that's not the final answer. Style points. Style points, one of the rules of style points is make the answer look like the original question. This answer here has a -3 in it. Didn't the original question look more like this? So what I'm now going to do and now we're finished. Okay. Now, I'm not being nitpicky here when I ask you to do style points. It's just good math to get into the format that you write an answer the way that typically all higher level mathematicians would expect that answer to be written, right? You don't want to kind of leave it hanging out there 3/4 done, right? You want to finish the job. And style points is like finishing the job. Make it look like the original. How about this fella? I want to find the antiderivative of 4 square root of x. I'm going to use the power rule, but that means I have to rewrite the square root of x as a fractional power. So isn't a square root a half power and a cube root is a third power and so on and so forth. Now, the power rule works for x cubed and x to the 5. It works for negative powers like x to the -4 and x to the -2, right? It works for them. And good news, it also works for fractions. And so the rule is the same. Add 1 to the power, 3/2. Now, divide by the new power. Isn't dividing by 3/2 the same thing as multiplying by 2/3? Right? Dividing by 3/2 is the same thing as multiplying by 2/3. So it's going to be 4 times 2/3, which gives me 8/3 x to the 3/2. Uh-oh. Style points. This has to look like this. What would x to the 3/2 look like if you returned it back into its square root life? What would 3/2 look
Square root
like?
of x cubed.
Now you're finished. There's a second reason why style points are helpful. Do you know that later on you are going to be plugging values in for x, like 1 and 12 and 2? Isn't it much easier to get the square root of 2 cubed or the square root of 12 cubed than it is to get 2 to the power of 3/2, or God forbid, 12 to the power of 3/2? Can you imagine how much trouble you're going to have trying to get the exact value of those? Because what you'd probably do is plug into a calculator and get 12.823, and we don't want that. We need exact values. So if you write it like this, you are much more likely to get the square root of 22 or square root of 40, which then turns into 2√10, right? You'll be able to get it in a much nicer format. Here's our next guy. The kind of ultimate version of what I just did. I'll make this 12. Do you think this thing's going to be a power rule? I just have to do some algebra to get it there. Huh? Agreed. Help me out here. What will 12 over the square root of x look like when written as a fractional power of x?
-1/2.
Now, add 1 to the power, positive 1/2. Dividing by 1/2 is the same as multiplying by 2, so now you have 24. And just like in every other question, at least almost every other question, doesn't that return back into the square root world? Now, every single one of these questions that we've done, couldn't you check that they were right by taking this guy here and differentiating them and see if you end up with that? Differentiate this and get that. Differentiate this and get that. It is possible to do that. If you are doing it correctly, you probably wouldn't need to check it unless you were one of those people who just wants to be, 100% sure. Do we feel comfortable about antiderivatives that use the power rule? Because that's really all we've covered right now. Feel good? Okay, I'm going to give you one to try out. A little bit different. The square root of x cubed. Two over x squared plus 3. Yeah, I'm giving you 1 minute. Go for it. No pressure. For those who need help, there's the powers of x that you need to turn 2 of them into. Last few seconds. Okay, I'll take a volunteer. You don't need to give me the style point answer because that's going to be after this line. You just need to tell me what, the halfway between there and there is. So a volunteer, what's the antiderivative of x to the 3/2?
The antiderivative of x to the 3/2 is 2/5 x to the 5/2.
Great. Add 1 to power, divide by new power. We'll fix that later. Right, next one. Somebody else, what would 2x to the -2 look like? Antiderivative of 2x to the -2.
-2x to the -1.
Correct. Add 1 to power and divide by new power. I'm doing this one because it's easy, right? 3x. Now, that's the answer, but as far as style points is concerned, doesn't this guy become the square root of x to the 5? Doesn't this guy become 2 over x? And don't forget your plus c. So as long as you use the power rule, and there's a good mixture of them, and we feel comfortable about that. Now, before we move on to other situations, here's some other things I want to introduce right now. You don't always get f of x. Would you agree that sometimes a function is called g of x or h of x? Things like that. The antiderivative, oops, is called capital G of x. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Boom, you got it. You also get functions where the variable is an x. F of u equals 6u cubed plus 1. If you want to find its antiderivative, it's called capital F of u. Add 1 to the power, divide by the new power, and simplify it. And you are done. So are you okay with the fact that it won't always be f of x? It might be g of x or h of x. It won't always be u. It'll be f of t, f of u, f of k, you know, some other letter representing the unknown variable. So far, so good. I'm just looking at faces to see if we're happy. Right. Do you want another joke? Because I don't think I got the reaction I was hoping. Would you like another joke? You're not so keen this time, Evan, are you? Bezida, do you want to hear another joke?
Yeah, let's do it.
Let's do
Sure,
it. Are you
let's do
ready?
it.
Okay. Now, Scotsman and his wife go on holiday to America, and they go to a state fair. And the Scots guy's watching this guy, and he has this little old-fashioned plane, and he takes people up, and he flies around the state fair, showing them it from the air. And he turns around to his wife and says, "That looks like fun. I wonder how much it costs. If it's not too expensive, we can do it." So the Scots guy goes over to the pilot when he's landed, and he goes over and says, "How much is it for me and my wife to do that thing that you do on the plane?" And he says, "Oh, it's $100 each." And the Scotsman looks at him and says, "Oh, no, that's too much money. I'm not paying $100. Not $100 each anyway. You want to make a deal?" And so the pilot looks around, and there's nobody else wanting to get on. So he's thinking to himself, well, you know, $100 is better than nothing. And he says, "Okay, I'll make you a deal. Just $100. That's it for both of you. But if I hear one shout or scream or anything, I want $200, the original fare." Scotsman says, "That's not a problem. It's a deal," and they shake on it. And it's one of those old aircraft where the pilot sits in the front and then the other two people like kind a piggyback behind him. And he takes off and he's doing his little circle round like he does with everyone else. And the pilot gets in his head and he thinks, "No, I'm not going to, I ain't going to let this happen. I want all my money." So he starts doing crazy things. He heads towards a mountain and at the last minute veers off. Nothing, quiet. He heads towards the ground like you're going to crash, and at the last minute he levels off. Nothing. He starts doing, aerobatic tricks. He flies upside down. He does loop the loops. He does everything he can think of. Silence. Nothing. So he gives up and he lands, and the Scots guy gets out and he goes over to the pilot and he gives him his $100, and pilot says, "Okay, a deal's a deal." And he looks at the Scots guy and he says, "You know, I tried everything I could think of to make you scream. It must have been very difficult to keep quiet." And the Scots guy nods and said, "You know, it was really hard. I almost screamed when the wife fell out."
All right, not bad. Not bad.
Yeah, that one was
Oh,
okay.
so
It was okay.
that one was okay.
Yeah, that's
You
one of my
realise
favorites of your
this is going
jokes.
to... it is one of mine as well, Michael. So, it's going to be a long 10 weeks. Just thought I'd tell you. Right, okay. Let's continue. antiderivatives. I think things are going pretty well so far. Let's look at some, oh, and by the way, I'm going to change the letters around in the things as well, just to be different. So, not the power rule anymore. We've left the power rule behind. We're going to do other stuff for a while. What's the antiderivative of 5e to the x? It's really just memory. If you remember how to differentiate, you should be able to find how to do antiderivatives. This is one of my favorite functions for finding antiderivatives or derivatives for that matter.
Isn't it just 5e to the x?
Yeah.
It is. So easy, you didn't think it was right. Isn't that a nice function to find the antiderivative of? Right? Nothing particularly happens to it. This question looks like it's a power rule question, but it is not. There is a function out there who, when you differentiate it, you get 4 over u. And that function has got nothing to do with 4 over u squares or anything that's even got a u in it in that sense. That's the most clues I'm going to give. Has anybody got an idea of what the antiderivative of 4 over u is equal to?
The natural log.
You got it. Can you remember that the derivative of a natural log is 1 over u, or 1 over x, whatever the variable is? So won't 4 of them be 4 over u? Now you might think, well, why can't I use the power rule? Let me show you what would happen if I tried to use the power rule. So this is the exception to use the power rule. Well, if I was going to use the power rule, I'd have to call it that, which is fine. Now watch what happens. Add 1 to the power. Okay. Divide by the new power. Doesn't that just disappear on you? Isn't 4 over 0 just not going to happen? Can you see why the power rule doesn't work for 2 over u, 5 over u, 7 over u, right? It works for everything else, right? 4 over u squared, power rule's great. 4 over the square root of u, nothing wrong with that. One exception, that exception. How about this fella? I'll return to my f of x. So these guys, you really just have to memorize. You just have to remember that the antiderivative of 1 over u is a log. So 4 over u is 4 logs. You have to memorize this one or just remember it. Antiderivative of a cosine.
Sine or like negative?
3 sine x.
Agreed. Right, let's check it out. What'd you get if you differentiate 3 sine x? Don't you get 3 cosine x? It's the right answer, isn't it? Now, some of you are looking at that and thinking, what about a negative? But you're thinking differentiation when you think that. What's the derivative of this? It's that. That makes this the antiderivative of that. What were you thinking, Evan?
Yeah, makes sense. Thank you.
Okay, let's do a g of x then. Antiderivative, right? Remember, it's antiderivatives we're doing here of 2 sine x.
Is negative 2 cosine x?
Yeah. isn't it like the opposite of differentiation? You get pluses when you get negatives, and you get negatives when you typically would get in pluses. Have you noticed that? That the antiderivative of a sine is a negative cosine, and the antiderivative of a cosine is a positive sine, right? Whereas if you differentiate, isn't it the exact opposite of what I just said? But that kind of makes sense, because isn't antiderivative the exact opposite of differentiation? So they should be different. This one is really going to test your memory. There is a function out there who, if you differentiate it, you get 1 over x squared plus 1, or in this case, 1 over u squared plus 1. Think of all the things that you have differentiated and what they were equal to. And think of one of them that when you differentiated it, this is what it was equal to. It is in
This
there if you go hunting
kind
for
of
it.
reminds me of, is it inverse tangent?
It isn't just is it in that kind of hesitant way. It darn is the inverse tangent. It is. Can you remember the derivative of the inverse tangent is this fella? And if not, maybe you should get a little sheet of standard integrals, standard derivatives. In other words, what the antiderivatives of various things are, and kind of study it for a while until it, gets back into your brain and it becomes part of your knowledge. Now that you've said that, does that ring bells that the derivative of a inverse tangent is that? Does that ring some bells? Okay, here we go. We'll go on to, well, let's do G if you haven't done that combination. Wow. I'll be impressed if anybody can remember this one. What's the antiderivative of 1 over the square root of 1 minus u squared? I'll give you a clue. It's an inverse trig function.
Is it inverse sine?
Nailed it. For completeness sake, what's the antiderivative of that guy? And the only difference is there's a minus in front of it.
Inverse cosecant?
Arc cotangent.
Just inverse cosine. It's the only difference. So we kind of left polynomials where I think you were pretty comfortable with, most of you. And now we've entered the antiderivatives of rare functions, right? Things you only see now and again. Trig functions like sine and cosine, and then some really weird inverse trig ones. But that's a pretty big bunch of functions now, isn't it, we can deal with as far as antiderivatives are concerned. So I'm now going to return back to polynomials. And I would like to find the antiderivative of x plus 2 times x minus 3. And what we sometimes have to do in questions, especially one like this, is to realize that the way it's written isn't actually conducive, isn't good for what I want to do. I want to do the power rule so I can get antiderivatives. And this isn't really written in a way that's going to make that possible. So what do you think I need to do first?
Foil it all out.
That would be what I would suggest. Now that I've done that, would you agree that this is a pretty standard antiderivative question involving polynomials? So its antiderivative would be add 1 to the power, divide by the new power, add 1 to the power, divide by the new power, and get that. So sometimes you have to do FOIL, distribute, whatever, right? Some algebra first, and then you can use the power rule to get the antiderivative. Suppose I wanted to find the antiderivative of that ugly fraction. If I left it in that form, I wouldn't really be able to do anything. So we have to figure out what other way it could be written that might help us to use the power rule. These three guys on the top, all over a u squared on the bottom. There's two different ways to approach this. Both of them work. Anybody get any ideas of either one approach?
Could you multiply everything by u squared?
Almost. I'm just going to change one thing. U to the negative 2. Right? Now, if you did it that way, oops, that's a 4. This guy times that guy is u squared. That's a bit messy, but it's doable. What would negative 2u squared times u to the negative 2 get you? What would, I'll write it down in case you're kind of visual learner. What would that guy times that guy end up being? Forget about the 2 minute. Oh, you said it, yeah. If you ignore that 2, don't these two combine to give you u to the 0? Isn't u to the 0 1, so you just get negative 2. And if you multiply this and this together, you get u to the negative 1. And this guy is okay for the power rule. This guy is okay for the power rule. This guy, however, isn't. Now he's good for the power rule. Antiderivative, add 1 to the power, divide by the new power. And this guy, oh, he's that log we did earlier today. Now, I said there's 2 ways to do that question. That way might not have worked for you. You might think that's a bit clunky. So let me show you essentially the same question, but a different approach. And this second approach, maybe it'll work a little bit better for the way your main works. Before I do it, does anyone know what the second approach is going to be? A totally different way of approaching this question. Any thoughts about how I could deal with this in a different way? Last
The
chance.
only way I can think of is you like bring up the u squared to divide each thing individually.
Okay.
Kind of like what we did when solving for the limit to infinity.
Oh, yeah, like divide top and bottom by u squared. Huh. That's essentially equivalent to that. I'm just separating it into 3 pieces, each with its own u squared. Now this guy is u squared. This guy is -2. And do you see how that one comes out just maybe a little bit nicer? And you're done. Are we cool with that one? So we are looking at antiderivatives of increasingly complicated situations. I'll only have time for one last question, so here it is. I want to find the antiderivative of that guy. Any ideas for a different way of writing that so I can use the power rule?
And just FOIL it out again.
Yes. It's really just the same guy times itself. And if you do a FOIL, you get 4x squared plus a 2x plus another 2x plus a 1. So you get a 4x squared plus a 4x plus a 1. And now I can use the power rule. Add 1 to the power and divide by the new power. Add 1 to the power, divide by that new power. 1 just gets you x, and then you're C, and you are done. That's actually quite good timing because we pretty much covered all the antiderivatives that we